I want you to try something with me for a second. If you can, just close your eyes.
Mm-hmm.
Imagine you're standing in the middle of a vast, open field. It's night. You are miles and miles away from the nearest city, so there is no light pollution, no street lamps, nothing.
Just pure darkness.
Just you in the dark. You look up, and you're expecting to see the sky you have known your entire life. You see the stars, the thousands of them, sharp and cold. You see the Milky Way, that beautiful dusty river arching overhead.
But something is wrong.
Something is deeply wrong. The sky feels heavy. It feels unnervingly, almost oppressively black. You scan the horizon for that familiar glow, the anchor that has guided humanity for millennia.
It's not there.
It's not there. The moon is gone.
And just to be absolutely clear here, we are not talking about a new moon phase where the satellite is just hidden in shadow.
Right.
We aren't talking about heavy cloud cover. We are visualizing a physical absence.
Yeah.
The gravitational companion that has orbited Earth for 4.5 billion years has simply vanished, or maybe drifted beyond its tether.
It's a genuinely terrifying thought, isn't it? We take it so for granted. It's just there, like the floor in your house.
Mm-hmm.
But if you remove the floor, you fall. So if you remove the moon, the questions start piling up immediately. Without that massive rock orbiting us, would the Earth just start to wobble uncontrollably?
Would the oceans go still?
Could human civilization, or maybe even life itself, could it survive such a fundamental shift in our planet's architecture?
These are precisely the questions we are tackling today. We are going to conduct a deep dive into the invisible architecture of our solar system.
Oh, okay.
We are going to treat this not as a fantasy, but as a simulation based on real orbital mechanics, geophysics, and planetary science.
And we're referencing the Eclipse Yardmaster Knowledge Core for this, right? To make sure the physics are sound.
Absolutely. The goal is to understand the incredibly delicate balance between stability and, well, chaos.
So let's unpack this. We're going to look at everything from the tides to the tilt of our planet. But I feel like before we can understand what happens if the moon leaves, we really need to understand how we got saddled with this giant satellite in the first place.
That's the right place to start.
Because when you look at the rest of the inner solar system, we are kind of an anomaly, aren't we? Mercury and Venus, they don't have moons. Mars has those two tiny captured asteroids.
Phobos and Deimos, yeah. They're potatoes, really, not spheres.
Right. But we have this massive object, one of the largest moons relative to its planet in the whole solar system.
We are absolutely an anomaly. The Earth-Moon system is often described by astronomers as a double planet system for that very reason. The moon is so large relative to the Earth.
A double planet. I like that.
And to understand why it might drift away, we have to look at the sheer violence of its birth. The prevailing consensus now is the giant impact hypothesis.
Ah, the big splash.
A very, very big splash. You have to picture it. Go back roughly 4.5 billion years.
The beginning of everything.
The solar system was a cosmic shooting gallery. It was a mess of debris, protoplanets, and gas. The Earth was young, molten, and likely still forming. And crucially, it was sharing its orbit with another protoplanet.
This is Theia.
We call it Theia, yes. A body roughly the size of Mars.
And Theia didn't stay in its lane.
It did not. Theia collided with the proto-Earth. And this wasn't a glancing blow. It was a cataclysmic, world-shattering impact that nearly destroyed our planet.
I can't even imagine the energy involved.
It liquefied the entire surface of the Earth, turned it into a ball of magma, and it blasted a massive amount of debris. Molten rock, dust, vaporized mantle material into orbit around Earth.
So for a while, Earth had a ring, like Saturn.
Exactly. A hot, angry, glowing ring of magma and rock. It must have been an incredible sight. But that ring wasn't stable.
Gravity takes over.
Over time, gravity did its work. That debris began to clump together. Bits of it coalesced, cooling and solidifying to form the moon. And this explains so much. It explains why the moon's composition is so similar to Earth's mantle.
Because it is us.
It is made of us. It is the scar tissue of a cosmic collision.
It's amazing to think that the serene white orb we see tonight is actually the result of such unbelievable violence.
It is. So fast forward to today. We have this satellite. It's sitting there at an average distance of about, 384,400 kilometers?
But here's the thing that really surprised me in the research for this. The moon is leaving us right now, as we speak.
It is. It's a slow process, but it's constant. The moon is drifting away from Earth at a rate of approximately 3.8 centimeters per year.
3.8 centimeters. That's roughly the speed my fingernails grow. It sounds completely negligible.
It sounds negligible to us because our lives are so short. We live for decades.
Yeah.
But on the timescale of the cosmos, of a planet, it is significant. It adds up.
But hold on, I want to pause on the why here, because this seems to break a basic rule. Gravity is an attractive force. The Earth is huge. The moon is huge. Shouldn't they be pulling each other closer? Why is it drifting away?
That is the beautiful counterintuitive part of this. It all comes down to tides and the conservation of angular momentum. It's a beautiful, is slightly complex dance of energy.
Okay, break it down for us.
Think about the tides. We all know the moon's gravity pulls on Earth's oceans, creating a bulge of water on the side facing the moon and the side opposite.
Right, high tide.
But here's the key detail. The Earth rotates on its axis much, much faster than the moon orbits the Earth.
Right. Earth spins once every 24 hours. The moon takes about 27 days to complete one orbit.
Correct. So now imagine that tidal bulge of water. Because the Earth is spinning so fast underneath it, friction between the water and the seabed drags that bulge slightly ahead of the moon.
Okay, I'm visualizing this. So the peak of high tide isn't directly under the moon. It's a little bit in front of it, in the direction of Earth's spin.
Exactly. So now you have this massive amount of water, this extra mass sitting slightly in front of the moon's orbital path.
And that bulge has its own gravity.
It certainly does. And it pulls on the moon. Because it is ahead of the moon, it pulls the moon forward. It's like a gravitational leash, constantly tugging the moon, telling it to go faster.
It's adding speed to the moon.
It is injecting a tiny amount of energy into the moon's orbit, constantly. And in orbital mechanics, a fundamental rule is if you make something go faster, it moves into a higher orbit. It pushes outward.
That makes perfect sense. It's like, okay, tell me if this analogy works. An ice skater spinning. If she is holding a heavy weight close to her chest, she spins fast. If she throws that weight outward, extends her arms.
She slows down. That is a perfect analogy.
So the Earth is the skater. The moon is the weight.
Precisely. We are transferring our rotational energy, our spin, to the moon. The moon gains that energy, which pushes it away, and in return, the Earth slows down. We are literally buying distance with time.
So our days are getting longer because of this.
Millisecond by millisecond, yes.
Right.
We are trading the length of our day to push the moon away.
Okay, so under normal circumstances, this is a very, very long goodbye. We're talking billions of years.
Exactly.
But for the sake of this deep dive, we are not waiting. We're going to simulate a sudden loss. Let's say we snap our fingers and the moon is effectively gone now. Or maybe a rogue planet swings by and knocks it out of orbit instantly. What is the very first thing we notice?
If we look at the immediate physical effects, the very first thing that hits us isn't in the sky. It's the water. It's the silence of the oceans.
The tides. Now, I think the common assumption is that if the moon vanishes, the tides just stop. The ocean becomes a flat lake. Is that accurate?
It is a very common misconception, but it is incorrect. Tides would not disappear completely.
Okay.
We have to remember that we live in a solar system dominated by a massive star. The sun also exerts a gravitational force on Earth's oceans.
But the sun is, what, 93 million miles away? Its pull must be tiny compared to the moon's.
It's much farther away, yes, but it is also 330,000 times more massive than Earth. Gravity is a function of both mass and distance, so it turns out the solar tides, the tides caused by the sun, are roughly 40 to 50% as strong as the lunar tides.
Oh, wow. So almost half of our tidal effect is already coming from the sun.
Yes, right now, when the sun and moon line up, during a new moon or a full moon, their gravity combines, and we get those extra high spring tides.
And when they're at a right angle to each other?
They partially cancel each other out, giving us the weaker neap tides. So if the moon vanishes, we're left with only the solar tides.
So the oceans wouldn't go flat, but they would get, well, a lot more boring.
Gentle might be the word. The variation between high tide and low tide would shrink drastically. In places known for their huge tides, like the Bay of Fundy in Canada or the Bristol Channel in the UK.
Where you see these massive water level changes.
That drama would just vanish. The churn of the ocean, that powerful mixing, would slow down significantly.
And this isn't just about surfing or building sandcastles. This has a huge biological impact, right?
Massive. Absolutely massive. Think about the intertidal zones.
The tide pools, all the life there.
Exactly. The coastline is one of those productive ecosystems on the entire planet. You have crabs, mussels, barnacles, kelp, small fish, entire food webs that have evolved over hundreds of millions of years specifically to handle that reliable rhythm of being submerged and then exposed.
We depend on it.
They rely on the high tide to bring in nutrients and oxygen, and the low tide to expose them to sunlight or different kinds of prey. It's a dance. If the tide suddenly stops retreating as far, that entire zone collapses.
What does that collapse look like?
Well, the nutrient exchange that happens because of strong tides pulling organic matter from the land into the deeper sea, that whole process would stall. This leads to stagnation. It's like turning off the circulation pump in a fish tank.
And that cascades up the food chain.
It cascades from the bottom up. When you disrupt the nutrient flow at the coast, you affect the plankton. When you affect the plankton, you affect the bait fish, then the tuna, then the sharks. And, eventually the humans who rely on the ocean for a huge portion of their protein.
So we're talking about a potential bottom-up collapse of the marine food web, all because the water got calmer.
Correct. The ocean is a dynamic engine, and the moon is a primary piston in that engine. You remove the piston, the engine loses a huge amount of power.
So that's the immediate effect on the water. But you said the more profound changes happen to the planet itself.
I did. While the tides are visible and dramatic, the long-term changes to Earth's rotation are even more fundamental.
Right, because we mentioned the ice skater analogy. The moon is acting as a brake on Earth's spin.
It's called tidal braking. That friction we discussed earlier, the tidal bulge dragging across the ocean floor, it acts as a brake. It slows us down, lengthening our day bit by bit.
And we know this has happened over time.
We do. In the time of the dinosaurs, a day was only about 23 hours long. Go back further, and it was even shorter.
So if the moon disappears, the brake is cut.
The braking mechanism vanishes. Now, to be clear, if the moon vanished today, Earth would just continue spinning at its current rate, 24 hours. We would suddenly speed up because of the conservation of momentum.
Okay, so we don't lurch forward.
No. But we would stop slowing down. Our day would be locked at 24 hours, effectively, forever. However, if we look at it through the lens of deep time, if we imagine a scenario where the moon had never existed in the first place, the difference is staggering.
How fast would we be spinning if we never had a moon to slow us down?
The models are pretty consistent on this. They suggest that without the moon's braking influence over Earth's 4.5 billion year history, our day might be only 6 to 10 hours long.
A 6-hour day? That sounds exhausting. You'd have, 3 hours of work, 3 hours of sleep. You'd barely get anything done.
The psychological impact on humans is one thing, but consider the physical environment of a planet spinning that fast.
Weather.
The weather would be unbelievable. A planet spinning that quickly generates incredible energy in its atmosphere, the Coriolis effect, the force that drives the rotation of storms like hurricanes, would be significantly stronger.
So the winds would be just insane.
We aren't talking about a breezy afternoon. We would likely see constant high-velocity zonal winds wrapping around the planet. Superstorms that make our current Category 5 hurricanes look like gentle breezes would be the norm.
The whole planet would be like Jupiter's Great Red Spot.
In a sense, yes. The weather patterns would be violent, rapid, and extreme.
So evolution would have had to take a totally different path. You couldn't have tall trees, they'd snap. You couldn't have long-necked animals.
Exactly. Life would likely be low to the ground, sturdy, aerodynamic, or perhaps complex life would have remained in the oceans, where it is shielded from that atmospheric violence.
That's a wild image, a flat, windswept world. But honestly, looking at the research, the wind seems like a minor inconvenience compared to the next issue, the tilt. This seems to be the part of the simulation where things get truly apocalyptic.
You are referring to the axial tilt, or obliquity. And you're right. This is arguably the most critical service the moon provides to life on Earth. It is our stabilizer.
So let's break this down for the listener who might not remember their high school Earth science. Why does the tilt matter so much?
Okay, imagine the Earth orbiting the sun. It isn't standing straight up and down relative to that orbital plane. It is leaning over. Currently, Earth spins at a tilt of 23.5 degrees.
And that tilt is the entire reason we have seasons.
Correct. Think of a flashlight hitting a basketball. If you shine the light directly at the equator, the energy is concentrated, it's hot. That's summer.
Right.
If you tilt the ball so the light hits the top curve at a shallow angle, the same amount of light spreads out over a larger area. It's weaker. That's winter. Because our axis is tilted as we orbit the sun, different parts of the Earth get that direct flashlight beam at different times of year.
So 23.5 degrees is our sweet spot. It gives us a nice mix of summer and winter, but nothing too extreme for life to handle.
And crucially, it is stable. It varies slightly. The research shows it wobbles between about 22 and 24 degrees, but it stays in that very narrow, predictable band.
And the moon is the reason for that stability.
The moon is the reason. It acts as a massive gravitational counterweight. The best analogy is a spinning top. If you spin a top fast, it stays upright and stable, but as it slows down, it starts to wobble more and more.
Okay.
The Earth is a wobbling top, but the Moon, because it is so large and orbits us, acts like a gyroscope. Its gravity exerts a constant, gentle torque that keeps Earth's wobble tight and controlled. It doesn't let us stray too far.
So without the moon, we lose the gyroscope.
We lose the gyroscope, and we enter the realm of chaos theory. You see, the Moon isn't the only thing pulling on Earth's bulge. We're also being tugged by the Sun and, most importantly, by Jupiter.
Jupiter, it's 500 million miles away. How can it have such an effect?
It is, but it is a monster. It's the bully of the solar system. Its gravity is immense. Without the stabilizing hand of the Moon to counteract it, the resonant gravitational pull from Jupiter and the other gas giants would cause Earth's axis to wobble chaotically over geological time.
We have an example of this, right? Mars.
Mars is our control case. It has no large moon to stabilize it. And because of this, Mars's axis swings wildly over millions of years, varying potentially from near 0 degrees all the way to 60 degrees. It's a climatic mess.
Okay, so let's play that out for Earth. What happens if our tilt goes to 0 degrees? So we are standing perfectly straight up.
If the tilt reaches 0, the axis is perfectly perpendicular to the orbit. And in that scenario, seasons vanish completely. Every single spot on Earth gets the exact same amount of sunlight every single day of the year.
That sounds, okay, boring, but livable.
It would be a climatic catastrophe. The poles would receive very little direct energy, ever. They would freeze permanently, expanding the ice cap significantly, perhaps down to cover most of Europe or North America.
While the equator.
The equator would bake under constant, unvarying direct solar intensity. The temperature difference between the superfrozen poles and the boiling equator would be extreme.
Which drives more of those superstorms we were talking about.
Exactly. But that is actually the better of the two bad scenarios. Consider if the tilt swings the other way. What if Earth tilts over to 80 or 90 degrees?
Like the planet Uranus, it basically rolls on its side as it orbits.
Precisely. If Earth did that, the North Pole would point directly at the sun for months at a time.
So if you're in the northern hemisphere,
For a quarter of the year, 3 straight months, the sun would never set. It'd be almost directly overhead, baking the continents 24 hours a day. Surface temperatures would soar to boiling levels. Meanwhile, the southern hemisphere would be locked in total freezing darkness for those same 3 months.
and then 6 months later, it completely flips.
It flips. The southern pole points at the sun. You would have continents that boil for 3 months, then freeze solid for 3 months. Agriculture would be completely impossible.
You can't grow crops in that.
No. Complex civilization, which relies on predictable seasonal rhythms for planting and harvesting, could not sustain itself. Most plant life as we know it could not adapt to such extreme and rapid thermal shock. It would be a climate catastrophe of the highest order.
It really highlights how fragile our Goldilocks status is. We think we're lucky because of our distance from the sun, habitable zone. But we're just as lucky to have this stabilizer keeping us from, tumbling over.
We absolutely are.
This brings us to a huge question then. If the moon hadn't been here from the start, would we even be here? Would life have ever gotten a foothold?
This touches on the very origin of life, the concept of abiogenesis. And there is a very strong scientific argument that the moon played a crucial, perhaps essential role in kickstarting biology on Earth.
How so? I thought the leading theory was that life started in deep-sea hydrothermal vents.
That is one very strong theory, but another leading one involves something called wet-dry cycling. For simple molecules to polymerize to form complex chains like RNA and DNA, they need to be dissolved in water to mix and interact.
Okay.
But then they need to dry out for the chemical bonds to properly form. They need a cycle of being wet, then dry, then wet again.
And the moon provides that cycle with the tides.
Not just any tides. Go back to that early Earth, 4 billion years ago. The moon was much, much closer then, perhaps only 20 or 30,000 kilometers away, compared to nearly 400,000 today.
It would have filled the entire sky.
It would have been terrifyingly large. And because the force of gravity weakens dramatically with distance, the tides back then would have been colossal. We are talking about tidal waves thousands of feet high,
Unimaginable.
rushing miles inland, stripping the land of minerals and chemicals, and then receding rapidly every few hours because the Earth was spinning faster back then, too.
A planetary washing machine.
There's a chemical mixer on a planetary scale. These massive tides would have cycled water in and out of tidal pools, dissolving minerals from the land, concentrating them as the water evaporated, then flooding them again. This rapid, high-energy cycle of wetting and drying is believed by many to be the engine that concentrated the primordial soup.
So the violence of the early moon might have literally churned life into existence.
It is very possible. Without that aggressive mixing, the organic compounds might have just stayed too diluted in the vast ocean. The soup might have been too watery, too stagnant to cook up anything as complex as life.
And even now, today, life is deeply tied to the moon. We aren't just talking about ancient history.
Not at all. We are all familiar with circadian rhythms, which follow the sun's 24-hour cycle. But many organisms also have circulunar rhythms.
Right, I've heard of this with coral reefs spawning.
It's one of nature's great spectacles. On the Great Barrier Reef, hundreds of species of coral release their eggs and sperm into the water on the exact same night, usually a few days after a full moon in spring.
They're all synchronized. But how do they know? They don't have eyes.
They have primitive light-sensing proteins, things called cryptochromes, that can detect the subtle blue-shifted light of a full moon. It's an ancient trigger. If you remove the moon, that signal is gone.
The synchronization breaks.
It breaks. If the corals don't spawn together, the eggs and sperm are too diluted in the water, they don't get fertilized. The reef dies.
And it's not just corals.
Oh no. Sea turtles use moonlight to navigate to the sea after they hatch. Millions of crabs use it for their migrations. Certain insects, even some nocturnal mammals, regulate their hunting and mating cycles by the phases of the moon.
So if you remove the moon,
You trigger what some biologists call a biosphere collapse. Food webs fracture. The entire rhythm of the biological world stumbles and breaks down.
it's incredible to think that a rock nearly 400,000 kilometers away dictates when a coral reef decides to have babies.
It's all interconnected.
Okay, now I want to address a fear that I think a lot of people might have if they saw the moon vanish. If we lose the moon's gravity, does Earth's orbit get messed up? Do we fly off into space?
That is a very primal fear, the idea of being cast adrift into the dark. But thankfully, we can look at the orbital mechanics for some reassurance here.
Good.
We need to look at something called gravitational dominance.
This goes back to Newton's laws.
It does. The equation for gravitational force depends on mass and distance. And in our solar system, the sun is the absolute monarch. It contains 99.8% of the total mass of the entire solar system.
99.8%. That's staggering. So everything else, Jupiter, Saturn, Earth, the moon, all the asteroids, it's all just rounding error.
Gravitationally speaking, effectively, yes.
Yeah.
The bond between the Earth and the sun is overwhelming. The moon does tug on us. It causes the Earth to wiggle slightly in its path around the sun. But if the moon vanished, that wiggle would just stop.
So our orbit would actually get smoother.
A tiny bit smoother, yes. But our overall trajectory, our distance from the sun, would barely change at all. We would not float away into the dark. We would stay right here in the habitable zone.
That's a relief. We keep our address.
We do. However, there is a nuance regarding the very, very long game. Without the moon stabilizing our rotation, there's a theoretical risk involving tidal locking to the sun.
Tidally locked? What does that mean again?
It means that one side of the planet would permanently face the sun. Just as the moon is tidally locked to Earth, we always see the same face of a moon-Earth could eventually slow its rotation until one side faces the sun permanently.
So one side of the planet is a scorching desert of eternal day, and the other side is a frozen wasteland of eternal night.
Exactly. Habitable life would only be possible in the twilight zone, a narrow ring between the two extremes.
Is that likely to happen?
I want to be very clear. This is a process that takes billions and billions of years. With the moon present, we are safe from this for a very long time. Without the moon, the process might accelerate. But even then, the sun would likely expand into a red giant and consume the Earth before we could fully tidally lock.
Comforting. We'll be incinerated before we freeze.
In astrophysics, you take the winds where you can find them.
Okay, so we've covered the physics, the tides, the tilt, the biology. This has all been very concrete. But let's shift gears to the human experience. Let's look at culture. If the moon vanished tonight, what does that do to us psychologically?
It would be a profound shock to the human psyche. First, consider the practical darkness. We are so used to moonlight. A full moon provides a surprising amount of illumination.
It really does. You can walk around outside without a flashlight.
It's enough to navigate by,
Yeah.
enough to see a predator, enough to cast shadows. Without it, the nights would be pitch black.
Save for starlight.
And artificial light, of course, but the wilderness would become a much more hostile, impenetrable place. But the deeper loss is cultural. The moon is a primary symbol in almost every human mythology and religion. Represents the feminine, the cyclical, the mysterious, rebirth,
Artemis, Selene, Changeothoth, it's everywhere.
and our calendars. The very way we mark the passage of time is lunar. The word month literally comes from the word moon.
Of course.
Our division of time into roughly 30-day segments is a direct reflection of watching the lunar cycle. If the moon vanishes, that ancient connection to the cosmos is just severed.
We lose the watchful eye in the sky. I think you're right. There is a psychological comfort in the moon. It changes, yet it always returns. It is constant in its inconsistency.
It is. If it's gone, the night becomes a void. It becomes an abyss, rather than a landscape illuminated by a quiet companion.
It's interesting how much comfort we draw from that big rock. It feels like a friend. Now, we have to ask the reality check question. We've been treating this as a simulation, but could it actually happen? Is there any plausible scenario where we lose the moon?
Well, we touched on the drift, the 3.8 centimeters per year.
The fingernail speed.
Right. That is happening, but it is far too slow to matter in human terms, or even civilization terms. The sun will expand and die before the moon naturally drifts away completely.
So it won't just wander off on its own.
Not naturally. The gravitational well of Earth is deep and strong. The only conceivable way to strip the moon from the Earth is through a violent gravitational interaction.
So something has to knock it away.
Something massive. We are talking about a rogue planet scenario.
A rogue planet. A planet with no star.
Exactly. Space is not empty. There are planets that have been ejected from their own solar systems during their chaotic formation, and they're just drifting through the galaxy in the dark. Astronomers estimate there could be billions of them in the Milky Way alone.
That's a terrifying thought.
If a massive body, say something the size of Neptune, were to pass through our solar system, its gravity could wreak havoc.
Like a bowling ball rolling through a game of marbles.
That's a great way to think about it. If the trajectory was just right, or just wrong, depending on your perspective, it could theoretically execute a gravitational slingshot maneuver on the moon.
It could just fling it away.
It could impart enough energy to the moon to break its gravitational bond with Earth, ejecting it into a new solar orbit, or even out of the solar system entirely.
Is that likely?
It is mathematically possible in a chaotic universe, but I have to stress this. Statistically, it is highly, highly improbable. Space is vast. The odds of a direct interaction like that are vanishingly small. But it does serve as a humbling reminder that our stability is not guaranteed by some cosmic law.
And that leads us perfectly into the philosophical side of this. We usually look for life out there by searching for planets with water or oxygen.
The follow the water principle.
Right. But this deep dive suggests we should be looking for planets with large moons.
This is the invisible stabilizer concept. We often focus on the habitable zone, the orbital distance from a star where liquid water can exist. But what if the habitable zone isn't enough? What if you also need a stability zone maintained by a moon?
You need a counterweight, a partner.
You need a partner. This connects directly to the anthropic principle, the idea that the universe appears fine-tuned for our existence because, well, if it weren't, we wouldn't be here to observe it.
It's a kind of selection bias.
It is. And when you look at the Earth-Moon system, it is a spectacular anomaly. We are small cosmic specks, but the specific architecture of our planetary system might be incredibly rare in the galaxy.
We won the cosmic lottery.
We did. It suggests that while simple life bacteria, slime, algae might be quite common on wet planets, complex, intelligent civilizations that require billions of years of climate stability might be exceedingly rare.
Because they need that lucky break. They need a big moon to hold them steady against the pull of the giants like Jupiter.
That's the idea. It forces us to confront the illusion of permanence. We look at the sky and think, this is how it is. This is how it will always be. But celestial mechanics teaches us that everything is in flux. Entropy is real. Systems evolve. The moon is leaving us, however slowly. Nothing stays the same forever.
It makes you want to go outside tonight and just look up and say thank you.
It really does. It reframes the moon completely. It's not just a nightlight. It's not just for poets. It's the flywheel of our planet. It's a piece of essential machinery.
So as we wrap up this deep dive, what is the big takeaway? What should the listener be thinking about when they look up tonight and see it?
I think the most powerful thought is this. We often romanticize the moon for its beauty, for the way it lights up a walk on the beach or inspires art. But it's true. Profound value is functional. It's mechanical. Perhaps the moon's greatest contribution is not its light in the night sky, but the quiet stability it has provided for billions of years, allowing life to flourish on a spinning, wobbling world. It is the silent anchor that allowed us to happen.
That is a profound thought. It's the silent partner in our existence. Thank you for walking us through the physics and the philosophy of this today. It's been fascinating.
It was a pleasure to explore the mechanics of our reality.
And thank you to you, the listener, for diving deep with us. I hope you'll never look at the moon the same way again. Look up tonight, appreciate that gravitational anchor, and remember just how delicate this all really is. Until next time.